structural scientist from the University of Maine in 1994. He's been working at the Gulf of Maine for about more than 20 years, and he's going to be telling us a little bit about it today. So.
All right. Thank you, Nikki. It's a pleasure to be here in the great state of New Hampshire. I'm not originally from New England. I've spent a lot of my life up here. I grew up on the coast of Virginia and North Carolina. Actually went to school with William & Mary, who I see is playing in football tomorrow. I wasn't even aware of that until today. And growing up and going to school as an undergraduate down there, I developed some rather simplistic ideas about sea level change, and that I had this idea or concept that it was a uniformly changing monotonic pattern that was related to the growth and decay of high latitude ice sheets. And after working in glaciated terrain for more than 20 years, I can look back on that and realize how simplistic that view really was. And today I want to it's half a historical perspective on what I've done for me, digging up some old slides and kind of bring you up to the present on what we've been doing here in the Gulf of Maine. Excuse me, my voice is just about shot. Talk of climate change is indeed everywhere these days. It's on the front page of your leading newspapers. It's soon to be in the halls of Congress again, I'm afraid, with Joe Barton and Darrell Weiss and others. There will be a lot of talk about what climate change is and what climate change isn't. Geologists, however, have known for many, many years this is a sea level curve from Fairbanks developed in 1989 from corals on the Barbados platform. And we've known for many years that sea level has done nothing but change over time. And this graph here, you'll see a number of these over the course of this talk, where we have elevation in the depth below sea level down. Sea level was about 120 meters below present, about 18,000 years ago, and it's risen at varying rates towards the present level. When sea level was low at the glacial maximum, the coastline was far seaward of where it is today. And large areas of the continental shelf were terrestrial. They were dry. And since then, as the ice has retreated and the water has gone back into the basins, sea level has risen at varying rates across this once emergent part of the continental shelf, what is now on the continental shelf. The rate of rise is anticipated by IPCC reports and others who conservative rates call for perhaps half a meter increased rate of relative sea level rise over the next 100 years, perhaps 50 centimeters. But plausible scenarios can call for up to 2 meters of rise over the next 100 years as rates of sea level rise accelerate. These are from Romsdorf and others. So the things that have driven my interest over the years is not only can we predict the rate of sea level rise, but how will the coast respond to these variable rates over time. And we've been in the last 5,000 or 6,000 years a regime of relatively stable sea level that's allowed deltas and barrier islands and spits and other coastal landforms to develop. And I think stable, I mean it's somewhat uniformly but slowly rising sea level. Tide gauge records today are already showing accelerations in the rate of sea level rise. So we're getting back into a period where sea level rise is starting to accelerate. The only real question is how fast will it rise? And can we then predict how a shoreline will respond to those increased rates of sea level rise? So as a geologist, the past is the key to the present. So we go into the recent geologic past to examine an area, the Gulf of Maine in this case, which has highly variable, both spatially and temporarily variable rates of sea level rise. So I'm going to start out today with just some introduction and background to the region and go through our most recent iteration of the sea level history in the Gulf of Maine and what the evidence for that history is, what we pin our points on, and then look at the impacts of those differing rates of sea level rise that we see in the geologic record, both on the shelf and along the coast. So the Gulf of Maine is a large, rectangular, semi-enclosed basin. There's a very complex tectonic history. At the last glacial maximum, the Pleistocene ice sheets were down here at the Cape, and the islands extended down to Long Island and across towards its banks about 20,000 or so years ago. And they retreated up across the Gulf of Maine, reaching the central uplands of Maine around 15,000. These are calendar years. I will mix up my radiocarbon in calendar years, but you'll have to call me on that. The overriding control on the shape of the coast and the shelf is bedrock structure and lithology. Jackson in the early 1800s divided the coast into different coastal compartments. We're located right down here off the map. And then in the southern part, southwestern part of the state, we have large arcuate embayments. The bays are generally underlain by metasedimentary rocks. The headlands are plutonic rocks, intrusive bodies. The indented embayments is a high-grade metamorphic complex, the Casco Bay group, with a strong northeast-oriented lineation to it. These beds are turned up on the end, creating these numerous long, deep waterways and estuaries. And as we move down east, we have, again, getting into the Island Bay complex, lower-grade metasedimentary and meta-volcanic rocks with intrusive plutons, such as the Mount Desert Island, forming large islands. And this high relief topography extends out onto the shelf as well. Now, this map by Clark and others is sea level change is not uniform around the world. I think we all recognize that. And one of the major controls is glacial isostatic adjustment. Sea level in glaciated regions that near where the ice margin was, isostasy is the dominant control on the relative sea level. Remember, we've got two things going on. We've got the water coming back into the basins. That's the eustatic sea level. And we've got the land moving up and down as well, either due to water loading or ice loading or sediment loading. And that is the isostatic component. So we have two variables going on. In Zone 1, these are glaciated regions. Beneath the glaciers, rebound is still occurring. The sea level, therefore, as the crust rebounds, sea level continues to fall. The land is emerging. You can see that in Hudson's Bay and parts of Scandinavia. Zone 2, which is beyond the margin of the glacier, say down in the Carolinas or Virginia, where I'm from, it's a zone of continual submergence because the eustatic sea level is flooding the landscape. Where we are today in the Gulf of Maine is this transition between continual emergence in the glaciated and the submergence in the more far fields. And these areas which are near the ice margin initially start out with a high sea level falls and then turns around and rises again. And this is the case in the Gulf of Maine, and we're going to take a closer look at that. Now, the concept is one of a glacial forebulge that as the ice loads the crust, it depresses the lithosphere. Sublithospheric material is pushed out to the periphery of the ice sheets. You can envision that if you take your hand and on the meat of your thumb and your fingers, the ice sheet. If you push down on your hand, you'll see that it's depressed in the middle, and you have a bulge of tissue that rises up around there. When you take that off, the subcutaneous material migrates back towards the center of the ice. Well, this is a cross section of this hypothetical forebulge. This is Zone 1, which is so the ice would be on the right hand side. So this is north, this is south. In Zone 1, glaciated regions here, as the forebulge migrates from left to right in this case, where you're located, whether it's, say, Hudson's Bay, the crust is uplifting you, so sea level is continually falling. Now in Zone 2, which is south of the forebulge, here's the peak of the forebulge, you're located here, the forebulge moves to the right, and it's one of continuous submergence. So your sea level is rising continually on this side and not on the other. Where we are in the transition is we're close to the crest of the forebulge, and as that forebulge moves under us, first sea level will fall, and then as we come up over the forebulge, sea level then starts to rise. So we have a lot of variation going on in the rates of uplift as well as any kind of meltwater events that might be superimposed on top of this isostatic signal. So this is a sea level curve from the Gulf of Maine, published by Joe Kelly and Dan Belknap and Stephen Clausen. I don't know if Stephen's here or not. He was at UNH for a long time. Some of you might know him. He's a marine archaeologist. And we'll look at some more of the work that they've done. But this is a sea level curve over the last 15,000 years. Here's present day sea level, the dashed line, sea level from a high stand fallen to a low stand, and then risen at varying rates to the present. You can see there's an uneven distribution of data points along this curve from about 11,000 or so. We have very good control. Before that, there's relatively sparse samples that we can date that have sea level information. So about 15,000 years ago, the ice had retreated to central Maine. At this point, the crust was depressed, had not yet rebounded. This was a marine transgression took place in contact with the ice. These were there is some debate over tidewater glaciers versus ice shelves, but the ocean was in kind of a tidewater ice margin. So as the ice retreated, it was an instantaneous transgression. It went from ice to very, well, maybe 50 to 100 meters of water instantaneously. As that ice calved off, the seawater moved right into it. And all along the upland shoreline, we have high stand deltas, shorelines, and glacial marine deposits. This is one example in Washington County, Maine. So this is an ice contact delta. You can see the kettle holes and other ice wasting features here. The ice was discharging water and sediment into the Gulf of Maine at this point, and the shoreline is about right along here. So this is a low-base, flat-top, Gilbert-type delta. Gravel pits in the front of this delta clearly show seaward dipping planiforms. These are the foresets, and the top set beds on top. This is a very carefully surveyed contact between the top set and the foreset beds, and that represents the elevation of sea level at the time of deposition of these deltas. So using these kind of a feature over, starting back in the 1930s, they basically defined this high stand shoreline, which was the maximum extent to which sea level rose at the end of the glaciers, at the end of the Pleistocene. Well, about 15,000 years ago. So this area in orange was all submerged. This was this is the gear C. The ice was discharging tremendous amount of fine-grained material, glacial rock flour into the gear C, forming very thick, widespread sequences of glacial marine sediment. This is the Presumpscot Formation. The type section is right outside of Portland, Maine. And it's very fine-grained. They make a lot of good pottery and bricks out of this stuff, too. But it's very widespread raised marine deposit, because after that high stand, as rebound accelerated, the crust started to pop up. We had very rapid sea level fall following that high stand. Between 15,000 and about 12,500 years, we dropped 60, well over 100 to 150 meters, depending on where you are, in just a couple of thousand years. On average, the rate, we're talking about 40 millimeters per year, which is really a dramatic fall. During this time period, marine sediments that were submerged are being exposed to terrestrial and river and other erosional processes. This is the kind of stratigraphy that you typically see along the coast. Bedrock is just beneath this layer of boulders, so this is till, which deposited beneath the glaciers. On top of the till, we have the glacial marine Presumpscot Formation. As sea level fell, this was eroded, formed a very strong unconformity on top of the glacial marine, and it's a very poorly drained. I don't know what it's like in Durham, but I imagine it's very similar, and which was very conducive to the development of bogs and swamps, and just poorly drained wetlands. And then there's a little bit of fill here on top. So we have the Pleistocene sequence of till, glacial marine, unconformity, and then the Holocene sequence on top of that. Again, just to show you this glacial marine clay, it was deposited very rapidly, and we have these these very rhythmically deposited. You can follow some of these reflectors across entire basins in the Gulf of Maine, and they drape up and over what is the bedrock knob right here. So very rapidly deposited, and we can follow those deposits offshore well out into the Gulf of Maine. And this is where I got really interested, because for many, many decades, geologists had studied the raised marine deposits, but very little was known about the submerged portions of it. So here's this is a boomer record seismic reflection profile. Again, depth and distance along the track line, showing high relief bedrock, a little bit of tilt, and these rhythmically bedded draping over the underlying antecedent topography. A strong nonconformity etched into it with a Holocene section of estuarine and marine sediment on top. We approached this mapping offshore. I'm going to date myself a little bit, because I started out using a lot of analog records and things, and now we've moved into the digital world. And it's really been a tremendous, the technology has really pushed the science, and vice versa, but I think it's more the technology pushing the science. And with a lot of our CCOM mapping work, we integrate sidescan sonar backscatter from sidescan, swath bathymetry from different systems. They're looking at the structure and stratigraphy using subbottom profiles. For ground truth, we have bottom photography, cores, samples, a lot of videos, and we really integrate all that. We basically integrate all that into what is now, we use a geographic information system to do our interpretive work and create geologic maps. We make all of these now, working at the survey, we make all of these now publicly available on websites. I mean, we actually deliver the processed data. If anybody wants the raw data, we can probably deliver that too. So this started in 1988, and to varying degrees, we've mapped from essentially the Canadian border down, and we're working south of Cape Cod now. This red area is from 0 to 60 meters. This is essentially the area that was emerging during the lowstand, and out to about 100 meters is where you got to draw a line somewhere. So we call the inner shelf out to about 100 meters, which isn't that far offshore. So about 15,000 square kilometers of seafloor, but the data quality, the data types, the data density really vary along this stretch. We've used any number of different boats, from our 26-foot Parker down here to large NOAA and this is Thomas Jefferson. This is our Parker. Various contract hires of boats. This is actually the University of Connecticut boat. But over the years, I've spent probably less time than Jim Barnhardt has, but I've been at sea hundreds and hundreds of days.
Not even
Yeah, but 100 days on that thing.
Yeah.
That's worth $1,000. And using these different data types. Initially, this is just a scan of an analog sidescan sonar record. Here's the center track line with port and starboard channels, and here's the vertical downward the vertical channel looking down. And we would basically use Loran navigation as best we could, lay these things out and draw polygons. And we would interpret this very broadly as a rocky zone. That was my idea. You know, it's really rocky, high relief, high backscatter. And cutting through these rocky zones, we'll have very large shelf valleys. These are valleys that were cut by rivers at times of lower sea level. So these are the kind of features that we were mapping, and we were producing maps of like 1 to 100,000, 1 to 200,000 kind of scales. Really regional scale maps. Well, starting in the early 1990s, working with a whole host of institutions here, and a lot of the people in the room. Larry's not here, but John Hughes Clark. It was the USGS in Woods Hole. It was the University of New Brunswick at the time. Larry was in New Brunswick, and the Canadian Hydrographic Survey mapped about 4,000 square kilometers of Stellwagen Bank and western Massachusetts Bay, using an early Rezon. I believe it was that was the Creed. What was it?
Transgression 950.
Yeah, that was in 1993. That was an old one. Yeah, it was the old Creed, the survey boat that they have, and they're doing about 16 knots. And we spent many years collecting and processing. This was really the first regional scale multi-beam survey, certainly in the eastern U.S. and one of the first in the world. It started in 1993. Since then, I've been working with the state of Massachusetts to then map a lot of the more shallow areas using small boats, using interferometric swath bathymetric systems, which are tuned for shallow water, to work largely inside the 3-mile limit of state waters. And this is being driven by ocean management issues, offshore wind energy, other resource management issues as well. And altogether, we've mapped in Massachusetts alone about, I want to say about 6,000 square kilometers at this time. And this has been recognized by, actually even some of our funding agencies have recognized this as being really valuable as a base map for studies of habitat, for studies of waste disposal in the ocean and other things. So it's really, and this is continuing. We're in the 3rd year of a 5-year agreement to work south of Cape Cod now. And ultimately, we hope to finish all of Massachusetts shallow water. When I say shallow, we go into about 10 meters. We cut it off at 10 meters. And then we try to fly LiDAR planes and things, but with a mixed bag of results, actually. We've actually had some good and some not so good. I think Shahak's been working with some of that with Seth Ackerman as well. To show you a sample of the modern, really high-res bathymetry that we're collecting now. This is with an interferometric SEA swath plus system, and for the first time, we've gotten to the resolution we can start to identify individual glacial moraines. In this case, offshore. This is Salem, Massachusetts. These were formed at the ice margin as it retreated about 14,000 years ago in this area, either stalled out or slight re-advances in this area. If we look at the superficial texture of it using drop cameras and things, the top of this till ridge, this bouldery till ridge, is a very large cleft and then spans out into sandy basin here. So this is the level of detail that we're starting to get into for generating maps for things like habitat studies. Okay, so back to the sea level story. So as sea level, as the crust continued to rebound very rapidly, it was rebounding faster than eustatic rise was keeping up. So you had an emergence to a low stand here about 12,500 years ago, about 60 meters deep. This low stand was very short-lived as the rate of rebound decayed and the rate of eustatic rise exceeded that value. It rose. It started rising, but at that bottom, during that finite amount of time that sea level was at that depth, we have a whole series of shorelines that were created at that depth, and we actually managed to date a small number of these. The big question was always, how old are they? And some of the kind of samples that we would get here, we have a species of shallow water barnacle, middle edgeless shells. Here's a pebble with some barnacles encrusted to it, and we got dates. This is in radiocarbon years, but the age of that low stand is about 12,500 calendar years before present. It was a very short-lived low stand. The rate of eustatic rise came to far exceed that uplift, so you had a relative sea level rise. And it was a very rapid rise at almost the same rate, about 40 millimeters over the course of the next 1,000 years. And about 11,500 years ago, we hit this plateau. And this is really where I'm headed, is this plateau here. So during that period, we have very little record of what was going on here. Sea level was rising so quickly, there was probably no time for coastal landforms to develop or anything else. But as we get into this, what we call the slow stand, from 11.5 to about 7.5, 4,000 years, sea level rose maybe 5 meters. So it went from very rapid to very slow. This is about half the rate of relative sea level rise today in the region. So it slowed down, and we have numerous examples of preserved salt marsh peaks and intertidal bivalves and all kinds of indicators of where sea level was at that time. So there's a high sediment supply, and we have shorelines and wetland habitats. Now this could be due, when I was in graduate school, I thought everything was isostatic, and I came up with a geophysical model of different core bulge configurations that came through, and I always called for this being an isostatic event. But really looking at some of the work that Kendall and others are doing, this could represent some kind of a global meltwater event as well. the jury is still definitely out on that.
What do you mean by that?
The
A large an acceleration of the melting or the...
Yeah, Kendall and others have been modeling, particularly with the Greenland ice sheet, and the gravitational attraction of seawater as the sublithospheric mantle material moves back towards the center of the ice. It actually takes a sum of seawater with it. So it's having not only an isostatic effect, but it's also having an effect, I guess, essentially on the geoid. So these are geoidal changes too.
Geoid rather than melting type of thing.
Yeah. Cores through some of these. Yeah.
That minus 60 meters seems to come in on some fairly weak evidence. For example, fractured seashells clearly can't be in place if they're broken.
The depth has never really been a problem because we have so many shoreline indicators. You know, I used to say it was at 55. But it's always been the age. It's always been what the age of these things. And so the samples themselves are not necessarily sea level indicative of the sea level, but the geomorphology is clear when you have these top sets, well, these cliniforms prograding out to the basin, for example, that leading edge of the delta, and you can see the fortsets within the delta and project that seaward. So the depth. You would quibble a few meters, but the age is always the problem. No, I'll concede that. And if you talk to Dick Peltier and others, he looks like this and say, you know, he's a geophysical modeler of glacial isostatic adjustment worldwide. And the first time he just saw it, he said that didn't happen. Next question. So these are observations. I really don't have I can't compete with him on how to explain it. But they're very strong. I mean, we have a lot of evidence. This is in shallow water, 26 meters, where we have cores of the Maya arenaria in estuary material overlying. This is the unconformity on top of glacial marine. Probably represented an analogous environment such as this. Tidal flats with small. These are all Maya arenaria here within the intertidal zone with small salt marshes and things. And we have hit basal peaks in these areas as well. So this plateau is well documented age-wise.
It also lasted almost 4,000 years.
It did. It lasted about 4,000, from about 11.5 to about 7.5 calendar years, and sea level rose maybe 5 meters, maybe 10. But it's a very slow rate of rise across that.
What are the models Peltier or others say about the length of that in terms of geoid adjustments or?
They really haven't addressed it directly. Peltier and Cushingham and Clark, and they use very large. They're doing whole Earth kind of models, and of course, this is it's a continental margin. There's very there's rift basins within this continental margin. There's all kinds of the geology is very complicated. There's a lot of faulting and complicated geologic structures in there as well. So it would be difficult to model from place to place. The thing about this sea level curve is it's all more or less located in the same location. This is from the recent publication by Kelly and Stephen Clausen and Dan Belknap from Mount Desert Island, located right here. It just came out in geology. And they, on a NOAA ocean exploration cruise, got blown out. And I forget what boat they were using, but they ended up going up into one of the bays, and they were going to survey something. And they had a multi-beam system, and they discovered a series of drowned shorelines. The local fishermen who had been pulling up these artifacts for years. These are adzes and spear points and all kinds of things, and they've been reporting these things. So this was just it was very low on their priority list, but it was blowing a gale, and it was in this sheltered embayment. So they went in and they found a series of shorelines, and that all they were clearly occupied by early humans. And these shorelines and the sheltered areas behind it all date from that slow stand area. So you can use this. You can use a well-documented sea level history to guide your exploration in terms of finding where stable shorelines in these wetland habitats that were attractive to early humans would be located. And I know Stephen's got some more work he's trying to get funded out there as well. Behind these, in this basin here, there were a whole series of of big round holes in the seafloor. This is a little bit of a digression. We could talk about pockmarks forever, but I feel like I always have to talk about pockmarks. This is a record I collected in 1988 using a towed side scan. And these are seafloor depressions on the order of a couple hundred meters across in either direction, maybe 30 meters deep. You know, the size of a high school football stadium, if you will. In cross section, they look something like this. Here's the bedrock of glacial marine, Holocene mud overlying these blanked out areas or natural gas within the sediments, and pockmarks are always attributed to the escape of fluids, whether it's water or gas, up through the Holocene, fine-grained Holocene, unconsolidated estuarine and marine material that resuspends and excavates these holes. We recently went back with some modern, again, the technology allowing us to do things that I never dreamed of doing. This is from John Hughes Clark in Blue Hill Bay. John Hughes Clark came down from UNV with his boat for a while, and this is from using our swath interferometric system in nearby Knobscot Bay. And there are literally thousands and thousands of these holes in the seafloor. There's a lot of speculation about what actually caused these. I think they probably represent, I mean, what caused the eruption of natural gas and or water, pore water, to produce these seafloor depressions. I suspect it was some seismic event, and these are essentially sand blows or mud blows, and they've been preserved. This is fairly cohesive material. I don't think they continue to leak gas over time, but they have 30-degree submarine slopes. This is a fine-grained underwater, so it's well beyond the angle of repose. But the current thinking is there's a reason Laura Brothers is just got her PhD working here in Belfast. She'd be a good person to invite her to talk sometime. Doing repeat surveys in here, really high res. I mean, now we've got the ability to go back with differential RTK GPS systems and really start to get down to the kind of centimeter level of repeatability. And look at, we did repeat surveys across here and saw absolutely, within the error of our uncertainty of our measurements, we saw no change at all. And we had an old NOAA survey from the late 1990s that we also processed to look in there. There were no new features, and there were no features that had been buried and disappeared as well. It's really an intriguing problem. But these occur up within the estuaries. The thought is that these probably represent old marshes and wetlands and lakes. So there's a lot of organic material that at the sea level low stand, when that was emergent, they had these wetlands up on what is now the shelf, but it was emergent. And that's where you got the thick organic material to produce the gas necessary to excavate these features. Well, since then, sea level has risen. It accelerated about 7.5 and it reached about, and worldwide we see a general leveling off of sea level rise around about 6,000 years before present. So we have a very complex pattern of sea level rise here that controls a lot of the coastal development. As you look offshore of these sandy beaches, this is an old side scan feature again. These are rippled scour depressions or sorted bed forms. This is essentially an eroded part of the shelf that shows patterns of essentially large sand waves moving along the coast that we collected. These sandy beaches exist offshore of large rivers. This is the Merrimack River, Plum Island. We got into again the modern era with swath bathymetry. Collected backscatter. This is you'll see a difference. This is backscatter collected with a Reson 8101. This is an SAIC survey that actually NOAA funded to go into about 25 meters, and then we work in shallow to about 5 to 10 meters. And this is from a towed side scan here. We collected a whole bunch of samples, video and still photographs, and we're generating these geologic maps at very regional scales. The yellow here basically shows this scoured platform that sea level rise. First it fell. The sea level fell to about 60 meters, which is essentially this contact between the yellow and the blue, and then it rose again. So this is seeing a regression and a transgression over the last 12,000 years. The next picture is just going to be that little square there. This is a close-up of the shaded relief bathymetry. You see a high relief feature on the seafloor there, overlay it with the backscatter. It's a high backscatter, high relief. I mean, this is not rocket science. There are some automated classification schemes. This is just a geologist drawing a polygon around a rocky zone here. And then we go back and test it. We look at it as large boulders. It probably represents an eroded glacial deposit, a drumlin, or perhaps a moraine. If you look at the subbottom profile over this feature, here's bedrock again, glacial marine overlying it, a little bit of till in this bedrock high. This is the transgressive surface of erosion that was formed during sea level rise. And this till basically just peaks out on the seafloor right here. So that was the subbottom is really key for us to interpret some of these features that we see on the surface. Now, surrounding it on the nearshore ramp, we have this is swath bathymetry and backscatter, and the high backscatter is yellow and red. The low backscatter is blue here, and we have these really irregular shaped patches of high and low backscatter. We collected samples across these transitions, and basically, if you look at a bathymetric profile, here's the low backscatter. Relatively elevated area. This is less than a meter of elevation of topography on the seafloor. And another one here. In the troughs, we have high backscatter, coarse sand, and these are essentially bed forms. These are sandy bed forms that are traveling across an extensive layer of higher backscatter, coarse sand, and gravel. So this is essentially the unconformity peeking out of the seafloor with bed forms moving across it. So this entire yellow area here is covered with those sorted bed forms or rippled scour depressions, and we want to look into the subsurface. So this is where really the sea level history resides. This is a chirp sub-bottom profile across this delta that was built out at the mouth of the Merrimack River. So as sea level fell, it's a regressive delta, and it's prograded out into the basin. And we have high relief bedrock, again overlain by glacial marine. And on top of that, we have a regressive delta. This is basically fluvial deposits that grade into the delta itself as it prograded out into the basin. You can see the four set beds within this delta here as it prograded out into the basin. Now, the delta was a silty, fine sand. It's very poorly dated. Again, this is a lowstand delta. We don't have a lot of good chronology on it. If you take a core through the top of this delta, again, this is the unconformity, deltaic sediment overlain by the Holocene. This is the mobile material within the system, if you will, and this is the transgressive unconformity, the surface of erosion. So sea level fell to about here on the delta and then transgressed over the top. So it's a very thin veneer of Holocene material, and then this coarse material is what's giving you the high backscatter patches. And where you have fine sand overlying that, as you move landward, this is the unconformity. This sharp line here, it thickens as you go up towards the beach. In this case, we can digitize that using SizeWorks or some other software where we actually digitize all these reflections and load them into a computer, and we create essentially an isopack. It's not even isopack, but it's a map of sediment thickness. This is the Holocene sediment above that unconformity, and this is we only did it in here in the near shore because we had a lot of data. The gray here is essentially zero thickness. This is the high backscatter material. You're looking at the top of the unconformity on top of the delta. And sediment thickness is thickest right here at the mouth of the river where you have a tidal delta, and as you move progressively to the south, it thickens up to about 9 meters down near Cape Ann. So this is Plum Island here, Newburyport, if you're familiar with it, not far from here at all. And so this indicates a long-term transport of sediment, basically from north to south along the system. This is corroborated by the geomorphic shape of the Plum Island as a prograding spit, the recurve spit is from the south as well. This is they have some real erosion issues down there, so we're starting to get into sediment budget type calculations. How much sediment is in the system, and what's the flux? What are the transport rates and pathways along the beach and any other eroding beach for that matter? And they're lucky here because they've got a lot of sediment. This is just in the Holocene, and there's probably many orders of magnitude more than this if you get down into the Pleistocene. So there's an awful lot of sand out there. Just take a look at a couple of sub-bottom profiles in the south. This yellow here, this is the Holocene sand on top of the unconformity. It's thickening from north to south in this case. Beneath that unconformity, you see right in there this incision of a channel that cross-cuts the contacts on the between the fluvial and the glacial marine material. This is a large channel. This is more than a kilometer across and about 20 meters, 15 to 20 meters deep on this location. If you strip out all that material, if you take off, this is a map of the topography on top of the glacial marine now. So all the Holocene has been stripped off. That channel fill material has been removed. And what it shows you is the location of these channels, which are incised into the Pleistocene. There's one big one here that I just showed you a profile across. And then there's another smaller system here, which has a dendritic kind of configuration with a main artery and smaller branches coming into it. And these were cut into the Pleistocene material when sea level was out in this location here somewhere. So the shoreline was out here at about 50 or 60 meters. The rivers and streams were incising into the glacial marine and discharging out into the sea. They've since been transgressed and backfilled. This is a profile across the three arms of that dendritic drainage here. Again, cut into the glacial marine, and they've been backfilled. And we recently got some cores from some of these features, and we hit some intertidal type deposits with juvenile mercenaria. We have a lot of oyster beds. We hit in situ articulated oysters in these channel fill, these incised valley fill complexes on top of the that are now buried beneath the delta surface. And they're all, again, within this age range, 20 to 23 meters, 9 to 10,000 years ago. The best sea level curve from Massachusetts was done by Bob Oldale many years ago, and he had a lot of dashed lines in here. He had very little data here, but he had none in here. And then it picks up with the salt marsh record about 6,000 and goes towards the present. If we plot these relative to the main sea level curve, which is very well populated, these fall basically right beneath that sea level plateau again. So it's not just a unique to the mouth of the Kennebec River. Now we're seeing the same signal, at least the beginnings of the same signal at the mouth of the Merrimack, some 100 kilometers or so south.
Walter?
Yep.
Quick question. You did it there, and you also did it in the main curve. Almost all your data points fall below the actual curve.
Mm-hmm.
Just so you can see the data points?
Not
that one here, but the one on Maine you have.
The one on Maine actually had some error bars associated. These are subtidal and intertidal, so we put it at some.
Oh yeah, no, that was fine, but I was just wondering, because the one in Maine, there's probably 30 data points in there, but the actual line, it could be a regression line. So
It's not a regression line. No, it's a.
So it's like a couple of meters above it.
Yeah.
Why is that?
Because these guys didn't live in the air. They lived beneath the sea level at that time. Yeah, and it's not a scientific adjustment. We had a group. we had a group.
We're geologists.
That's right. Now when we get up into this part of the curve, and then we have foraminifera and other critters that have very well quantified living ranges and different species. Very down to they're trying to squeak centimeter level kind of resolution out of it. You go back this far on a ship with a core, and so you say that's good enough. I don't want to over-interpret the data at all, but I know what you mean. We've gotten criticized about that before. Okay, so I'm going to finish up here really quickly. Just a conceptual idea of what might have happened at the mouth of the Merrimack. Here's the present-day Plum Island, and here are these channels which are filled with old estuarine deposits that are very similar to what exists behind the island here today. Same kind of environment. It's very analogous. If we take that feature and move it seaward out to 20 or 25 meters of water, now we've got when sea level was lower, 9,000 to 10,000 years ago, what is now open ocean shelf. We have a sheltered back barrier estuarine type environment. The propane spit here is anchored to that rocky zone that I talked about briefly. To anchor it, and the major outlet is to the south. In this case, there may have been some breaching event here, and this may be even older as we get deeper. I'm not sure what to make out of that. But this is very much similar to what we see today. Here's Plum Island, the mouth of Merrimack, and right at the tip of Plum Island, we have a big eroding deposit of till and boulders. So Plum Island itself has been pinned or reinforced, if you will, at the end to this glacial deposit. Now, what's going to happen when sea level continues to accelerate? This is a drumlin here, and I believe there's some up in here as well. How is that system going to behave? Is it going to roll over itself in that classic tank tread model, or is it more of a saltation or a jumping barrier? Is this thing going to erode when the sediment supply is depleted from this eroding drumlin and then reestablish itself back here, probably in a big storm? That's what I think that's what a lot of people see coming. I didn't come up with this hypothesis at all. This is one of Duncan Fitzgerald's students working down in Cape Cod Bay. This is Duxbury Spit, and here are old drumlins that exist out on the shelf. And he hypothesized, even back then, even with a lot less data than I have, that there was a barrier existing seaward of it. It has since transgressed to its present location. The sea level continues to rise. He anticipates that it will reattach itself along these other two existing drumlins in Plymouth Bay. So anyways, that covered a lot of ground. I went a little bit longer than I had hoped to, but y'all are very patient. So just in conclusion, there's a number of geologic controls on the coast. Bedrock is a first order control, glaciation, but after glaciation, it's really been sea level rise, sea level change, we'll say, both fall and rise, that has controlled the evolution of the shelf and the coast. And that sea level signal is dominated by glacial isostasy over the last 15,000 years. We've seen a transgression in contact with the ice, then a rapid regression followed by a transgression at varying rates across the shelf to create our current stratigraphy, our lake quaternary stratigraphy that we see out there. These submerged shorelines that exist at a couple of very discrete depths, one along the low stand of about 50 or 60 meters, and then there's some other shorelines, and this is all across the region. I didn't show a whole lot of them, but there are some shoreline features in about the 20 to 30 meter kind of a water depth in these sheltered areas, such as the work that Joe Kelly did around Mount Desert Island and Blue Hill Bay. And we're starting to see that this is really a consistent regional pattern. It's not just data from one location where we have a lot of data points to draw a line above it to some degree, but we're starting to see it in other locations around the Gulf of Maine, and we're hoping by doing that, if we can get enough well-constrained sea level histories to be able to say something more about the amplitude and the wavelength and the rate of migration of this forebulge, but also the impacts of eustatic changes in eustatic sea level rise. I mean, as we start to see climate warming and sea level rise accelerating, we can make some projections about how some of these barriers will behave, barrier shorelines will behave. But anyhow, thank you very much. Is that Chuck?
Following the last slide, you showed the total of sediment transport. When you say something about the currents in the Gulf of Maine and how they change or stay constant during the sea level change?
The currents, the shallow, along shore currents and things. Well, there has been a fair amount of modeling that's been done as sea level rise. The sea level rise has overtopped George's Bank, so the tidal current certainly varied a great deal. And you had, and that would be Roland Garrels, who's in Durham, England, actually. He's a salt marsh guy, and he's done some modeling of changes in tidal amplitudes due to overtopping of George's Bank and enlarging the connection with the North Atlantic into the Gulf of Maine basin. The storm patterns, I think there's a lot to be said on how storm patterns have changed since the last glacial maximum. I'm not that familiar with it. But one thing that certainly has changed is the amount of fetch. At the Merrimack River, for example, you have a large featured what's that ledge that goes off of Cape Ann? Jeffries Ledge. Jockey's Ridge is in the Outer Banks. Jeffries Ledge, a large intrusive plutonic body, probably the extension of Cape Ann, extends and hooks around off of the Merrimack River. So at lower sea level, that would have reduced the fetch tremendously. So the wave energy at that time would have been a lot less. In fact, there are shoreline features all along the leading edge of that ledge as well. And that was a major pinning point for the Pleistocene ice sheets. If you go to Gloucester, it's a dog town. You see the Dogtown moraine. I mean, the ice sheets really got pinned on Cape Ann and Jeffries Ledge. So I don't know if that answers your question or not, but I think there's a lot of variability in there.
You didn't say anything about crustal tilting. You might explain some of the differences between Massachusetts, New Hampshire, and Maine. You just sort of lump them as though there's no tilting.
There's a whole range of it. The elevation increases. The elevation of the high stand shorelines, the elevation to which these ice contact deltas are graded to increases from north to south. And I think in Massachusetts, the high stand at Byron Stone is correct. It's about 33 meters above present. And if you go further up into central Maine, it's maybe 120, 130 meters above present. And I didn't get into that at all. There was a tilting effect. You had isostatically depressed crust like this, but as the ice melted, the crust, it didn't rise straight up. There was more depression at the center where the ice was thicker, so it was actually the land surface was tilted. So you had this differential uplift. And they have drawn iso lines of uplift as you go from north to south, or from southwest to southeast to northwest, I guess. And there's been a lot of discussion over what some of the discrepancies between these elevations might represent, such as well, maybe you can explain it better than I have, but you know, one of the reasons I moved offshore, it was a very well populated question at the time. But these shorelines are tilted as you move from the south back towards the center of glaciation. And we just don't have enough data offshore to be able to really have a couple of delta, and they've all been beheaded by the transgression anyhow, so we don't really have that preserved top set, four set contact that's so clearly indicative of sea level at the time.
This was great. I just enjoyed this enormously.
Oh, I'm glad.
Have you done anything with funding and maybe GSC people? Tidal loading and funding, for instance, are tied right now, but obviously at lower sea level, there was not that tidal loading because funding was a river.
Mm-hmm.
I always wondered about that amplifying, engulfing your
down. Well, with the Gulf of Maine Bay of Fundy system, we're really at that resonance point where the harmonics are just about perfect, and the period of the incoming tidal signal is more or less matched to the harmonic of the basin. I'm probably not doing a good job explaining that, but if you were to lower sea level, you wouldn't be in such you wouldn't have that amplification, that resonance that would occur. So there, as sea level has approached that perfect position, the tidal amplitude in Bay of Fundy has gone way up, and that's one of the things that they've been trying to get at. If you're looking at old salt marsh, and you're looking at the high marsh, low marsh contact, for example, but the tides back then were a fraction of what they are today. They represent a very different sea level than you might otherwise come up with. But in the Bay of Fundy, they're talking about putting hundreds and hundreds and hundreds of tidal turbines out there, and what they're finding out is the tides are really big and they got a lot of sediment, and what happens when your turbine gets buried? So, I mean, it's remarkable what they're proposing to do in the Bay of Fundy. I don't know if it'll ever fly or not. They've gotten away from building a dam across the Minas Basin, and so that would have increased the tidal resonance, I think. And they modeled that sea level or the tidal range in Boston would increase by a few tens of centimeters or something if they lopped off the Minas Basin. That was back in the 70s when they were going to do that. Now they're talking about putting turbines on the seabed generating a lot of power.
You made a comment earlier in your talk about the isostatic rebound is basically still going on in Scandinavia and the U.S. And yet you look at that curve, and that would suggest that it's pretty much over in this part of Maine.
I think so. I think
so. It's happening farther to the northwest. Where is isostatic rebound continuing today in North America?
If you look at, and this is an old slide. I threw this away right before I was just getting too long. These are all in radiocarbon years, so the years are just before we started doing all this calibrations and everything. But here's the main sea level curve here. If you go to Nova Scotia to work at Ralph Stage, he's got a sea level low stand of about 65 meters, a little bit earlier. Up in Quebec, so here's 12,000. Here's 10.5, which is now 12.5. Now I don't know what that would be in calendar years, but you know you're getting progressively. If you're interpreting that low stand as the crest of the four-bolt moving through, at least the pattern fits that is consistent across three different ice. As you go up ice towards the center of glaciation. Going around the island of Newfoundland, I think Newfoundland is probably about the hinge point where you've got subsidence on one end. I read a paper recently. I can't remember the woman's name, but she was working in salt marshes, and she thinks she's seen tilting of Newfoundland. That maybe that's about where the hinge is. I'll have to go back and look it up. But anyways, it is traveling back towards the
well, yeah, I mean, it's logical to actually become asymptotic to your zero line.
Mm-hmm.
It just struck me that it's pretty much there.
Well, if you really zoom in, you really zoom into the salt marsh record, and then you get into smooth liners versus wigglers. And Orson von der Posse would have had every little point, and then it would look like a sawtooth. And other people like, I'm more if it was smoother. I tend to, think that a lot of that might be just noise. But yeah, I think it's pretty much over here, and it is now up in more in the Gulf of St. Lawrence region. Again, based on very little data, which is the All right. Well, thank you very much for having me.